Okay, so welcome to this video. In this video, I'm going to talk about solar cells in parallel in a module, and I'm going to show you how to calculate the current voltage characteristics if we have several solar cells in a parallel connection for a module. So let's get started, first of all, with the circuit diagram we are going to consider. So we have three solar cells here, shown by these symbols, and these three solar cells are in a parallel connection. If we have a parallel connection, all the three solar cells have the identical voltage, that is, the voltage over solar cell 1 is equal to the voltage over solar cell 2 is equal to the voltage over solar cell 3. Also, if we have the parallel connection, we know that at this node here, the sum of all the currents has to be 0, and we see we have the currents 1, 2, and 3 entering the node, the current I exiting the node, so the total current I of the module is I1 plus I2 plus I3 for such a parallel connection. In all of the calculations I'm going to show you in this video, I'm going to assume the simple diode model as shown here. So we just have the photo current source here, and we have a diode in parallel. Of course, you could also do the same kind of consideration with other diode models or even with experimental IV characteristics. So for these videos, I'm going to consider for this simple diode model. Okay, so if we now calculate what the IV characteristics look like, this means that we have, first of all, for one of the solar cells, the curve shown in yellow here. And this is the current in amps over the voltage in volts. And we assume a photocurrent of 2 amps for each of the three solar cells. So all of the three lines are lying on top of each other. That's why we only see the third one, the yellow one here in this case, and the blue and the red line are just underneath this yellow line. So all the three solar cells have exactly the same IV characteristics as shown here, calculated by the simple diode model. Now, if we use the circuit equations, that means if we want to calculate the total IV characteristics, all we have to do is to sum up the currents at a given voltage. So, for example, if we are right at the beginning here at a voltage of 0, so we are considering the short circuit current, then that means we have 3 times 2 amps, and that is exactly equal to the 6 amps for all of the three solar cells in parallel. Then if we go to other points, of course, if we are here at the open circuit voltage, then all the voltages are equal, all currents are 0, so the total current is 0. And if we are somewhere in between, we just multiply 3 times this current to get the total current. Now, if we want to know what the power is of these parallel connection of three solar cells, we need to multiply the current by the voltage for each of the voltages, and then we obtain the graphic shown here. So again, for just one of the solar cells, we have the yellow curve, and all the three solar cells are equal here. And then for the overall, the total current multiplied by the voltage, we get the purple curve shown here. And if we look at where the maximum power point is, we see this given here by this cross. We see that the maximum power point is at the same voltage, always at 0.72 volts for the individual cells and for the total module, summing up all of the different currents. And regarding the power that we get 1.36 volts for each of the solar cells and a total of 1.36 watts and a total of 4.08 watts then for all three cells in parallel. And also, if we just compare this now, the sum of P1 max plus P2 max plus P3 max, that is the sum here, P123 max is also 4.08 watt. So 3 solar cells in parallel, if they have all the identical characteristics, that means then that the total module has 3 times the power of each individual solar cell. So the module power P total is equal to the sum of the powers of the 3 individual cells if all the cells are identical. Now let's look at the case where the cells are not identical. So here now I have the scenario where we have 3 cells with 3 different photocurrents, 1 amps, 2 amps, 3 amps, and you can see that the 3 individual IV curves correspondingly are at different positions due to the different photocurrent. And now if we want to calculate what the total characteristic is, again we need to sum up the 3 currents. So at the short circuit current here, we have 1 amp plus 2 amp plus 3 amp is 6 amp for total. And we can do that for each voltage here and get again the purple line as the total line here. The most interesting part of this curve is probably the region down here, and I extended the graph a bit more to the negative. So here you can see the graph running up to minus 2 amps, such that we can see all of the lines. So the blue line is then for voltages that are smaller, that are larger than 0.8 volts. The blue curve is actually negative, while the other 2 curves are positive. And if we sum up the voltages, that means that the total current here, this purple curve, is cutting the yellow line because the blue line is a negative value, the yellow line is a positive value, and then also the red line is a positive value, and then the sum of the 3 is approaching 0 and crossing 0 right here at this point. So therefore, we can see now that this blue curve here, or the solar cell 1 that is running at 1 amp photocurrent, so that has less incident sunlight, this is actually in this region here not generating current, but it is a consumer. That is, it is driven by the other 2 solar cells. So that is of course not what we want. We want solar cells to be generators, so to generate power, not to consume power. And we can see here that in this region, where for the blue cell the current is negative and the voltage is positive, it is a consumer. But then we're not going to run the solar cell in this region here. But if we are looking at where the maximum power point is, we again multiply U times I, so the current by the voltage to get the power. And here we can see the 3 power curves or power voltage curves for the individual solar cells, and we can see the power voltage curve of the overall combination, so parallel connection of the 3 solar cells. And now we see that we want to run the overall parallel connection of the solar cells here at this voltage of 0.72 volts. That's where the maximum power point is, and we get a maximum power of 4.08 watts at this maximum power point here. If we now compare this to the sum of the 3 individual powers, and here I'm giving also the values of the 3 individual powers and at which voltage they occur, we first of all see that the maximum power point for each of these curves is now not at the same voltage any longer. We see that curve 1 has the maximum power point at 0.69 volts, curve 2 at 0.72 volts, and curve 3 at 0.73 volts. So that means we cannot run all of these 3 solar cells simultaneously at the maximum power point, because for the module, if they are in parallel, the 3 solar cells, it means they all have the same voltage. So we cannot be at the same time at the maximum power point of cell 1 and cell 3 and cell 2 also. Actually, what we find out is that the maximum power point of the overall cell is at 0.72 volts, so corresponding to this middle voltage here. If we compare the obtained power for the total cell is 4.08 watts, and that's slightly less than the 4.1 watts that we would obtain for just having the 3 cells separately and having them as separate generators and running each of the cells at the maximum power point. And this small difference comes from the fact that we cannot run all 3 cells at their maximum power point. So because of that, we lose a bit of generated power if we do a parallel connection of 3 solar cells. So in this case, where we don't have the same IV characteristics for all of the 3 cells, it means that the total power is no longer the sum of the 3 individual powers. Actually, it's a bit less, as we saw. So we get less power if we do a parallel connection. But you can also see it's just a little bit less. It's quite a little loss that you have due to not running all 3 cells in the maximum power point here in this parallel connection. And the parallel connection, of course, is advantageous to not have to have all the electronics for each of the individual solar cells, but to have joint electronics then for this module going onwards into the electricity grid. So let me show you the program quickly that I used in order to calculate these curves. Okay, so this is my program in order to calculate the IV curve of a parallel connection of 3 solar cells. So what I'm doing here, I'm as usual defining the constants I use, and these are just abbreviations to call such that NA nanoamp is, for example, 1 × 10⁻⁹. Then I'm defining my voltage range that I want to use in the calculation, and I'm actually introducing this variable precision, which I set to 0.002 volts in order to be able to quickly change with which precision I'm doing the calculation. I have my 3 different cells. Here all the cells are set to 2 amps, so same photocurrent. And then I have the parameters for the simple diode model, so the ideality factor of 1.5, the temperature voltage of 25.9 millivolts, and I set the saturation current for here to 1 nanoamps, so 1 × 10⁻⁹ amps. Subsequently, I just calculate the 3 currents using the diode equation in combination with the parallel current source, photocurrent source, following the simple diode model. So now I1, I2, and I3 are the currents of my 3 individual solar cells, and then for a parallel connection, the total current is just given by the sum of the 3 currents. To calculate the power, I first of all calculate the power of each of the individual cells, which is just the voltage multiplied with the respective currents. And then I calculate the total power by multiplying the voltage with the total current as I defined it up here. Okay, so then finally I want to also find the maximum power point, and I actually just find it here from the array. That's why the precision is then coming into play. So here I just calculate where is the maximum power of the vector P1, and then the maximum power value is the P1 max, and the index of the maximum power value is the II max 1 here. And this I do for the individual P1, P2, P3 values, and also for the total power. I use this max function in order to find the maximum value of the total power. And finally, I'm only plotting everything. So in order to plot it, I do one figure for plotting the individual curves. So this is plotting the IV curves. Then I'm plotting the maximum power points here. And I'm just defining where I want to look at. So here I'm looking at a region from 0 on the y-axis to the I total, to the maximum power times 1.2, so maximum of I total, and label the whole thing. And then I generate here my legend string. This is in MATLAB, so depending on which program you use, this will of course look a bit different. But for MATLAB, you can generate a legend string by using the num_to_string function. And then I just have here, I say that I want to plug in the value of I photon 1, so the value of this variable, into the string given here. And this nomenclature with the percentage sign 0.1f means that here the I photon 1 value of the variable should go in float format with 1 decimal after the comma. And so this I do for all 3 photocurrents. And then I plot the power voltage curves, and here I do the same thing. I first of all plot the 3 individual power voltage curves, then I plot the maximum power point or cross as a point here. So this kx means it's a black cross. And finally, I again enter here this legend string, which is again a bit longer. Here I do it as a cell instead of using the nomenclature I did before, which is a different option of doing it. So here I define the legend strings as a cell array with 5 elements, and then I put into each of the elements here the string, and I change to this because I want to put in 2 variables, the maximum power as well as the voltage at which power this occurs. And then I get here that P1 max is here I plug in the value of P1 max given back here with 2 digits, and it's at the voltage of, and then here the voltage value at the maximum power point index is plugged in volts. And that is the whole thing. So let's run this. And if we run this, it should generate the 2 figures, and here they are already. So here we have our figure of what the IV curves look like. Here we have our figure. Here we have our figure what the power looks like, and we can extend it a bit in order to see it a bit larger. And this is, of course, for all the identical IV curves. And then we can do the same thing by switching here the values around. So, for example, if I go here to 1, 2, and 3, for example, or let's take a bit smaller differences, 1.5 and 2.5 to see a different example. So I run it again, and now here are our 3 graphs. Here we have our 3 IV graphics again. You can see they are now closer than before. And if we look at the power characteristics, so here we have the power characteristics now, and we can actually see that if they are close together at here, as shown here with just 0.5 amps difference respectively in the photocurrent, the maximum power is still the same as the sum of the 3 individual powers to the 2nd decimal place. Okay, this is it regarding the parallel connection of solar cells in a module. See you for the next video looking at series connections.